Hi, and welcome to Advanced Power Plant Design. This is the first lecture in the course, and this is the instructor, Nick Siefert. This is the course that's taught at Carnegie Mellon in fall 2014. And these slides were going to be kind of a motivation and overview to everything that we're going to be covering in this course, as in why we need fuels and electricity and how we generate fuels and electricity in a way that doesn't emit CO2 into the atmosphere. Okay, so in advanced power plant design, this course is going to be mixing together a number of different engineering specialties, such as chemical engineering, where we're going to be looking at reactions, kinetics, process flow diagrams, CO2 absorption, CO2 deabsorption, and other gas separation processes. All these kind of fall under what's typically called chemical engineering. But we're also going to be looking at things that fall under mechanical engineering, such as pumps, compressors, turbines, and heat exchangers. And as well, we're also going to be looking at things from the engineering economic side, such as how do you estimate capital, labor, fuel costs, how do you calculate the net present value, the internal return on investment, or the levelized cost of electricity. So this class is going to be combining all three of those disciplines. And the general schedule of the class is we're first going to be looking at equilibrium thermodynamics, which is kind of the question, how much electricity could you in principle generate from the fuel and air if you had an infinite amount of time for this reaction to occur, right? That's equilibrium thermodynamics. Next in the course we'll be covering kinetics, which is really sometimes called non-equilibrium thermodynamics. Means how quickly does the reaction or process occur, and if you have a certain amount of time for a reaction to occur, how much power do you actually generate? Because you're going to end up generating less than if you had an infinite amount of time to wait for the reaction to occur. And then the third part of the class is what we call system modeling, which is how do you put the individual components of the system together to calculate the overall net electricity from the power plant, or other things of interest, maybe the net heat out or net chemicals out. And then finally, at towards the end of the class, we'll be getting into the engineering and economics, which is really how do you optimize and how do you ultimately answer the question, does it make sense to build this power plant? So to continue with our overview, I'm going to be talking and describing a little bit about our non-equilibrium world. We live in a world far from equilibrium. In classes, you might have often heard about pressure and temperature in equilibrium environments, but when you look at things globally, not everything is the same temperature and pressure. So the world is not at equilibrium, right? So what we're doing, and by we I mean human beings or other animals or life like bacteria, what we're doing is taking advantage of non-equilibrium environments to generate useful work. And we generate the useful work as we move part of the system towards the equilibrium. So what we're doing is we're using useful work to help us find more non-equilibrium systems in which we can then generate more useful work, right? So ultimately the goal is to use less useful work than you can generate after you've found some more non-equilibrium systems, right? And so this non-equilibrium kind of cycle is maintained by the sun, though of course currently fossil and nuclear fuels are the dominant source of work on Earth. And just to reiterate how non-equilibrium our world is, if it were in equilibrium, the world would be at the same temperature, meaning at thermal equilibrium. It would be the same nuclei, meaning it would be at nuclear equilibrium. And this is a question to ponder that I'll get into later, is if it were in nuclear equilibrium, which nuclei would it be? Also, everything would have to be in the same chemical state, or at least they'd be chemical equilibrium. And then everything would be at the same pressure, mechanical equilibrium. So in such a world, the world would be extremely symmetric. And that's not our world. We're far from equilibrium. So in this course, you'll be introduced to the concept of Exergy. We'll spend an entire week covering it, but for now, just want to point out, hit on some of the main points that I want you to get out of when we finally do the full weekend on this topic. And it's one of the main points is that energy itself is conserved. Right? Energy itself is not created or destroyed. It can take different forms. Right? It can be in thermal energy. There can be thermal energy. There could be potential energy. There could be electrical energy. Right? But ultimately, when you add up energy in a system, and for the entire universe, it's ultimately conserved. Now, there's this term called Exergy, and we'll be learning using it throughout the course. The Exergy actually is something that is either constant or decreases with time. And typically what we're talking about when we're talking about energy is we're actually really using the term Exergy. And Exergy is defined as the maximum useful work that can be generated by bringing a system into thermal, mechanical, and chemical equilibrium with its surrounding environment by means of a reversible process. By reversible, I mean a really slow process. Okay, so Exergy destruction is the loss of work potential due to irreversible entropy generation. In this course, we'll be using the symbol sigma sub IRR to mean the irreversible generation of entropy. So these two figures here, first one we have a pendulum one, and that was the point of that graph is just to point out the fact that energy is conserved. It's just that it goes in between gravitational potential energy when the ball is at its highest point. It's purely gravitational potential energy. At the lowest point, it's purely kinetic energy, and then it goes back up to being gravitational. It just goes back and forth and back and forth. And energy in this process, in a simple pendulum, is conserved. It's neither created nor destroyed. It just goes from one form to the other. However, in real thermodynamic processes, you'll have work entering or heat or work entering a system, and you'll have some amount of heat and work leaving. But ultimately, there's always some small amount of Exergy that's destroyed if you do this in a finite amount of time. If you could wait an infinite amount of time, you could avoid that sigma IRR. But if you try to do it in a finite amount of time, you always end up destroying some Exergy. And that amount of Exergy, as we'll see later on, is equal to the temperature of the environment times that sigma irreversible. Okay, so let's talk a little bit more about Exergy and how that, in relation to the Earth's environment. And what I'm showing you here is some graphs done by a group out at Stanford. And what they did was they tracked the flow of Exergy as well as the reservoirs of Exergy here on Earth. So in their graph, what they have is, if you see flows, here meaning like these open arrows, or arrows in general. The flows are in units, that's the Exergy flux in units of terawatts. That's 10 to the 12th watts. So what we're seeing here is that the Exergy coming from the sun and solar radiation is 162,000 terawatts, right? That's when it's coming in. That's during the day when it's coming into the atmosphere. That Exergy, some of that gets reflected and actually comes off as light. Some of it gets absorbed in the oceans or on land. And if you see in this graph, anytime these little triangles with the hashes across it, triangles with the hashes is locations where there's Exergy destruction. So if you notice, there's very, very little Exergy destruction with the reflection off the atmosphere, right? Because it's sunlight coming in, or high sunlight here being high energy photons, and when it scatters, it's still high energy photons. So the capability to do work did not change. And just as a reminder, the temperature of the sun near its surface is about 6,000 degrees Kelvin, right? So the average temperature of the photons that are hitting the Earth are around 6,000 Kelvin, right? Much, much, much higher than the room temperature of 300 Kelvin, right? So if you plugged 6,000 Kelvin into a Carnot efficiency, you get effectively 100%, right? 1 minus 300 over 6,000 is essentially 1. So what we're seeing here is that the photons have a large capability to do work, right? But as soon as they get absorbed by the sun, by the land or by the ocean, most of that exergy goes away, right? It's been converted into into a temperature of 300 degrees Kelvin, which is IR radiation. And that act of being converted from high energy photons to low energy photons destroys exergy. Now, it doesn't destroy all the exergy. Some of the energy goes into waves, wind, right? Evaporating the surface, which eventually causes rain, and that rain. So the wind energy, the wave energy, and eventually the rivers, we can generate electricity from that. And it's actually as we see here, the wave energy is 60 terawatts. I mean, that's a large amount. Wind is 870 terawatts. Right? We're not using, and the hydroelectric in the rivers is another 4 to 7 terawatts. Right? And we're not using hardly any of that right now. There's still a lot of room for growth in that area. Okay. Now, of the 162,000 terawatts, only 90,000 terawatts is used in photosynthesis. And then that gets stored ultimately in biomass. So anytime you see these little humps or lumps, those are reservoirs of exergy. Like in plants, that's the biomass has the capability to do work. And those units are in gigajoules. So it's 10 to the 21 joules, right? We're talking about very, very, very large numbers here. And so of the 90 terawatts of biomass, about a tenth of a terawatt is actually used in commercial biofuels production, right? And then we also have these stored reservoirs from biomass from millions to thousands of years ago, which are in the form of coal, oil, and gas, and even methane hydrates. And right now, we're only using very, very small amounts in terawatts compared to the gigawatts. If you see how, gigajoules of stored coal, oil, and gas. Right, there is thousands of years of coal and oil and gas under the ground. There may not be thousands of years of economically viable coal, oil, and gas, but there is still large reserves of coal, oil under the oil and gas in the Earth's crust. Right. Enough to significantly affect the concentration of CO2 in the atmosphere. That's one thing I want to point out here. We could significantly impact the CO2 concentrations if we actually went after that 270 gigajoules of coal. Okay, and then we have other sources of reserve exergy, and that'd be crustal thermal energy. Basically the fact that the Earth's a little bit hotter deep underground than it is at the surface. We could take advantage of that. Or we can take advantage of the stored nuclear exergy in uranium or thorium, right? Or if you notice here, there's also thorium in the seawater. And then the other ones pointed out here are the lithium and deuterium. And if anyone knows, the reason this group has included lithium deuterium is that if you combine lithium and deuterium, you can create 2 helium species, which is the plan for nuclear fusion. Okay. Now what we're going to do is I just want to briefly show some flows of energy. Here, energy being not necessarily the capability to do work, but it's what's called like the higher heating value of a fuel. And I just want to give you a feel for processes here in the U.S. And here the units are in quadrillion BTUs, which are also called quads, which is conveniently about 10 to the 9th gigajoules. So what we have here is you can see we're largely using coal and then natural gas in the electricity sector. Very little petroleum is being used in power plants, and then there's a sizable amount of nuclear and then a somewhat sizable renewable. That renewable is mostly coming from biomass and hydroelectricity today. In the future, we'll definitely see more of that coming from wind and solar. Of that input into the power plants, actually the majority of the higher heating value of the fuel is lost in what we call conversion losses, i.e. Exergy destruction. And then of the remaining, it gets used either in residential, commercial, industrial applications. Okay. This is a graph from Lawrence Livermore National Labs, kind of showing the same thing where we have energy supply into the U.S. economy, and then shows how much of that actually gets used in electricity, how much of it gets used into transportation, and then how much of the electricity gets used either in the residential, commercial, or industrial applications. And once again, it shows how much energy gets destroyed, what they're terming the rejected energy. Okay. One thing I want to point out, if you saw in those last kind of slides, is that the graphs are very linear type of thinking. It's like energy input in and then useful energy output. And one thing I want to convey in this course is that that linear way of thinking will not help you actually try to build power plants, right? Because you will miss what the actual point of a power plant is. So in order to think more like power plant designers and like living creatures, we need to think like living creatures, right? Right. The point of the bacteria is not just to take sunlight and turn it into ATP, right? Right? The point of a power plant is not just to create electricity, right? So what I'm trying to point out here is that the living systems have a cycle, we'll call this biospiral growth, right? Growth feeds off the generation of one product is used to make another product, but ultimately it creates this entire cycle in which the whole system is growing. So some of the simple parts of the, let's take a bacteria, right? The bacteria is going to have multiple components. It's going to have its factories, which are the Golgi apparatus, right? These are the factories making structures for the cell. We've got the chemical plant, which is making a ribosome, which is used throughout. Right, we also have the power plant, right? The mitochondria or the chloroplasts are making the ATP, which are used in the factories or the chemical plants, right? And we also have to have fuel itself, right? Bacteria is not going to be able to survive if it doesn't have some kind of a combination of sugars or some kind of chemicals, right? And sunlight. It needs an Exergy source, the fuel, right? And when the bacteria is working right, all these systems have to be working in combination, and then you can get the bacteria to actually grow. Okay. So I thought I would just quote from a Stuart Kauffman book that came out in 2008. Stuart Kauffman's a biologist and physicist, and I thought he had the best way of explaining this kind of this strange loop that life is. So I'm just going to quote from it just to, because I thought his words are better than any I could do myself. So here we go, in Stuart Kaufman's words. Cells do a combination of mechanical, chemical, electrochemical, and other work cycles in a web of propagating, organizing of processes. Given boundary conditions, physicists state the initial conditions, particles and forces, and solve the equations for the subsequent dynamics, i.e. the motion of the piston. But in the real universe, we can ask, where do the constraints come from? It takes real work to construct the cylinder and the piston, place one inside the other, and then inject the gas. It takes work to constrain the release of energy, which when released constitutes work. This is part of what cells do when they propagate organization of process. They have evolved to do work to construct constraints on the release of energy that in turn do further work, including the construction of many things, but also construction of more constraints. Indeed, cells build a richly interwoven web of boundary conditions that further constrains the release of energy so as to build yet more boundary conditions. End quote. The additions into that quote are mine. And what I want to convey here is that I just want to repeat the main point of this is that cells use work to build the constraints that allow them to build more work. And that's what I mean by the biocycle of growth. Right? And ultimately, we're here as engineers. The point of this course is to cover some of the things in what I'll call the core cycle that's required for growth. Right? And that's the fuel, the factories, the chemical plants, and the power plant. And in this course, we're going to be focusing on the power plant. But we're also going to be briefly touching on some of the other aspects, such as the chemical plant and the fuel. And when combined with the factory, these are what I call the core parts, the core requirements for growth. And when the core is able to grow, you can I'll say, when the core, you can use some of the products that would be used in the core, that would be used for growth. You can kind of sap away from that for other definitely required parts, which are, let's say, the arts, defense, medicine, science, and other parts of science engineering, like the research parts of it. Right? But if the core itself is not able to grow, you can't in any way sap from it in order to provide for arts and defense and medicine and science engineering. And it's really easy to construct cores that are not capable of growth. Right? And right now, if you tried to build a solar power plant in, let's say, Minnesota, that had to also be the chemical plant and the factory that built the solar plant, don't quote me on this, but I do not believe that you actually have a self-replicating cycle, right? We do have self-replicating cycles when the power plants are coal, the fuel is coal or oil, we have chemical plants, and the factories all run off of the electricity from the power plants or from oil or coal or natural gas. We know that not only is it self-replicating, but you can sap from it to provide for arts and defense and medicine and science and engineering. What we've yet to demonstrate is that we can have a core that doesn't emit CO2 that can also be sapped from for needs such as arts and defense and medicine and science and engineering. And that's what I see as the crucial challenge for engineers of the future, is how do we build the core that is non-CO2 emitting, that is also capable of growth and capable of being sapped from for all the other requirements that we have in society. So basically, let me state this one more time. How do we continue to grow in a carbon and other pollution constrained world? This is the way I see it. The problem is not a lack of energy or a lack of exergy. The problem is that there's a lack of growth in those countries that are tackling the issues of greenhouse gas emissions and pollution. And those countries that are growing, right? The countries that are growing aren't tackling the issues of pollution and greenhouse gas emissions. And then even worse, there are countries that aren't growing and aren't even tackling pollution issues. So let me quantify some of these statements. So what I have here is a graph based off of data from the British Petroleum Statistical Review of World Energy of 2013. And what I'm putting here is a graph of useful work generation in terawatt hours. Right? Useful work generation is here, it's the sum of all the electrical work being generated, plus a sum, added to that is all the mechanical work and being generated in a country. Mechanical work being work done by cars and trucks, right, to overcome friction. So what we have here is the U.S. is in blue. The U.S. economy in this sense has the largest amount of useful work generation. Followed by that is China, and you can see a steady but rapid increase from between 2000 and 2012, so that if that trend were to continue, China would, in a few years, have a economy that generates more useful work than the U.S. After that is Japan and Russia. We've got India, which is starting to take off, and then after that we have countries like Germany, Brazil, France, and the UK. So let me put this graph also in terms of the average yearly rate of growth of the sum of the mechanical and electrical work between 2000 and 2012. And when you see this graph, what you see is some numbers such as 10.3%, which is China's yearly average rate of growth. India's is 5.1, Brazil's is 4.0. Russia is the next largest with a 1.2. And if you notice, this is the what's called BRIC: Brazil, Russia, India, China. These are the countries that have greater than 1% growth rates. You can see all the other major economies have growth rates on average between 2000 and 2012, which are less than 1%. And in some countries like the UK are actually negative. They're actually shrinking in that sense, as far as their generation of useful work. Now, so this is the problem statement. We have near zero, but of course, the countries that are trying to tackle CO2 emissions, right, are all those ones with essentially zero growth, right? So how the problem we stated is, how do we increase growth and the capability to do useful work without somehow damaging the environment or emitting more CO2 into the atmosphere? And that is the challenge, and that's part of what this course will be addressing, is how do we fix that? Right? How do we get growth rates back up in places like the U.S. And how in places like China do we keep growth rates high but start addressing pollution issues? Okay, so of course we have to answer the question, why do we want growth, right? Or why do we want growth in GDP or in people or whatever it is? And one way to put it is, there's a strong correlation between the generation of useful work and GDP, right? The way to put it is, new technologies, of course, increase the demand for electricity. And in some sense, power really is knowledge, right? If we want to have a society that is able to operate particle accelerators like CERN or Fermi, or if we want to have a Hubble Space Telescope or the International Space Space Center, right? We need electricity. If we want to have computers and cell phones, right? All these things require electricity. If we want to be able to visit, Mount Fuji, if we want to be able to go hiking, camping in Alaska. All these things take large amounts of electricity or transportation fuels. Right? If we want to start populating other planets, right, we're going to need large amounts of fuel and electricity to build the equipment, the space vessels needed to go to other planets. These things aren't cheap, right? They all require real inputs. So if we want it, the only way we can do that is if we can continue to grow our economies. So what I'm doing in this graph over here is showing the correlation between the GDP and the amount of useful work, right? The other way to put it is there's a near one-to-one correlation. It's not exact. There's some countries that seem to like Russia and Canada, that don't seem to fit on the graph very well. But other than that, basically what this is saying is that an economy is, or one way of measuring economy is its capability to do useful work, right? In the sense that if I try to measure the amount of bacteria in a petri dish, right, I'd go around and I'd count the bacteria, right? But in that case, it's a pretty simple, I just go around and I can't count the bacteria because each bacteria is exactly the same as the others. In an economy, no one power plant is exactly like another power plant. So you can't just go around and count the number of power plants, right? But what you can do is you can go around and count the amount of power generated by power plants, right? And it's effectively, that's the same way as just going around and saying, counting bacteria and saying how many, you measure the growth in the bacteria by counting the growth in the number of the bacteria. Here we're measuring the growth in the economy by the growth in its capability to do useful work. Okay, so now let's talk about the pollution issue. We could always just build coal power plants, right? So the question is, why is that not, it might be a short term, there might be some short-term gains from building a power plant, these coal power plants, but the point of this section is to point out why there's some very long-term problems with doing that. So, of course, here are some of the major pollution issues. We have particulate emissions, right? Major problem right now in China. Oil spills, major problems in the Gulf coasts. Oil spills coming from North Dakota when trains derail. We have toxic chemical leaks. All right, we just had a chemical leak in West Virginia, and people affected the water supply, and now people have to go to using bottled water. Right. This waste storage accident. This is a graph that's a house, I believe, in Kentucky, where a coal ash containment pond, the wall of the pond broke, and the pond flooded the houses downstream of the pond, and just completely destroyed these houses. It's basically coal ash that house is surrounded in. There's other issues that in the U.S. we've largely tackled, but are still definitely issues in other countries. That's acid rain coming from NOx and SOx emissions. And of course, the big one, which we'll cover in this class, which is global warming due to the increase in greenhouse gas concentrations in the atmosphere. Okay, I do want to point out, since this class is in Pittsburgh, that air pollution definitely can be an issue, but we won't be covering this. There are other courses here at CMU which cover air pollution. But I just want to point out that the air quality in Pittsburgh has been greatly increasing. When I first taught a course, Pittsburgh was the American Lung Association had put it as the most polluted U.S. city for year-round particulate pollution. It has now dropped to 8th in its 2013 study. And this graph over here, showing in a Pittsburgh-Newcastle region, which is where we are in, you can see that the particulates average concentration has been steadily dropping, and hopefully in the not too far future, we'll get to the point in which it's not a major health concern. But it's still going to take a few more years before that's the case. Right now, of course, the places that are most polluted as far as particulate are all located in California, and that's mostly coming from a combination of cars, power plants, and then unique weather, or places where weather can be trapped. And that's part of the reason why Pittsburgh has been bad in the past, is that the hills create places where weather formations like clouds can just get trapped. And as opposed to, it'd be very hard to keep air pollution around in, let's say, Nebraska, where there's no hills, essentially. Okay, so let's get into the major topic that will be covered in this class, and that's greenhouse gases in the atmosphere. Just want to do an overview of the types of greenhouse, like what are greenhouse gases, a little bit of kind of the physics behind it. So what I'm going to start off with is the composition of the atmosphere. And the composition being about 78% nitrogen, 21% oxygen, and then you can have between, let's say, 1 and 4% water vapor, about 1% argon. Of course, these numbers aren't adding up to 100, but this is the numbers in black are on a dry basis. They add up to 100 if you don't include the water vapor. And then we've got a 400 ppm of carbon dioxide. And we have much smaller amounts of noble gases like neon, helium, krypton, and then very small amounts, ppm levels of methane. Now, in black, what I've shown are gases that are either atomic or diatomic, symmetric diatomic. So, in order to absorb in the IR, what you need is an asymmetric vibrational mode. Right? So let me say that again. In order to absorb in the IR, you need an asymmetric vibrational mode. So, of course, atomic gases like neon, argon, helium, they don't have any species to vibrate with, so it's impossible for them to absorb in the IR. Okay. So then we have the dominant gases like nitrogen and oxygen. Luckily, these cannot absorb in the IR, or else we would have a super, super huge greenhouse gas effect, and life would not, life as we know it would not be possible. Right? So the reason that nitrogen and oxygen do not absorb is that they're symmetric. Right? The bonds increase and decrease, but there's no asymmetric, there's no net dipole that can ever be created that can couple to the electromagnetic field. Right? When the oxygens pull apart or come together, there's no net dipole. Okay, now with water vapor can actually have 3 different asymmetric vibrational modes, right? And this is part of the reason why water vapor is the largest greenhouse gas in our atmosphere. One is just the sheer amount of it, right? We've got percentages of water vapor. The other is that it has 3 asymmetric modes of vibration. The next largest greenhouse gas is carbon dioxide, and that's partially due to its 400 ppm, but it only has 1 degree of freedom. It has 2 asymmetric vibrational modes that can absorb in the IR. 1 degree of freedom for each of those. So it has two modes, and so you can see CO2 is not going to be as important as water vapor. But as we'll find out, CO2 can last in the atmosphere for much, much longer on average than water can. So it can have quite a large effect on temperatures. And then finally we get to methane. Now methane is only 2 ppm of methane, but it can actually have a sizable effect because it has 2 asymmetric vibrational modes, but each of those 2 asymmetric vibrational modes are what we call triply degenerate. So there's really 6 modes that are available, right? And so this means methane is going to have a lot of different places. It could have a large, it has the potential, even though there's only ppm levels of it affecting the temperature on Earth. And then one way of putting all this is that what typically is calculated as something like a 50 or 100 or some amount of years global warming potential, and it's called the GWP. And then you compare it to CO2 to show how effective one molecule is compared to carbon dioxide as far as its global warming potential. And this global warming potential takes into account the number of asymmetric vibrations, whether or not they're degenerate, multiple, let's say triply degenerate, and then it also takes into account how long that gas species on average can last in the atmosphere after it's emitted, let's say by a power plant or by a person or by a cow, right, in the case of methane. So for methane, its 100-year global warming potential is 25 compared to CO2. Nitrous oxide is about 300. And then you've got these hydrofluorocarbons, which can have global warming potentials of like multiple thousands. Here's one that has 14,000 compared to carbon dioxide. Of course, there isn't going to be much of it, but it doesn't take much hydrofluorocarbons or CFCs to really cause, if you put as much hydrofluorocarbons as you put CO2, we would have really strong change in the absorption in the IR, and that would really strongly affect temperatures here on Earth. One thing I want to know is that the global warming potential of water vapor is not normally calculated. Okay, so I kind of talked to you first about what greenhouse gases are. Now I kind of want to go through the explanations of how we know it's human combustion of fossil fuels that is actually causing an increase in the greenhouse gases and hence a change in the temperature. So let me walk through some of the how this case has been with a case for human-induced greenhouse global warming. So what I have here on this graph is the CO2 concentrations in the atmosphere. You can see that they're increasing from 1970 about just over 320 parts per million, and they are now at the 400 ppm level. Okay, but during that time, the oxygen concentration in the atmosphere was actually decreasing, right? That's how we know that, right? This isn't just CO2 is increasing because it's coming from CO2, CO2 in the earth, right? If the oxygen is also decreasing by the same amount as the CO2 is increasing, we know that the CO2 is coming from carbon, right? It's not coming from CO2 from volcanoes, it's actually coming from carbon. Right, so that's one case where we clear evidence that it's human-induced emissions of CO2. Okay, another one is that the isotope ratios are changing with time. The isotope ratios are another sign that it's fossil fuels, and it's not like this biogenic emission of CO2 from some kind of recent process. Right? The fact that the carbon isotopes are changing with time is a clear sign that this is fossil fuels that are being burned. And of course, we largely suspect that it is humans that are, it also matches up with the amount of fossil fuels that are being burned by humans. So let me give you a feel for, you've probably seen some of these graphs before, but the concentration of carbon dioxide in the Earth's atmosphere, for thousands of years, it kind of fluctuated between 200 and 300 ppm. And then it's only been in the last century that it went from about 280 ppm to 400 ppm. And this, in the 400 years, this is unprecedented. Now, it's not unprecedented in history. There have been times where carbon dioxide concentrations have been in thousands of ppm, right? And life still survived, right? These are times in which there's life on Earth with large amounts of carbon dioxide. But if you went back to that slide, it's the rate at which this is happening that worries people, including myself, right? When you have millions of years to adapt to changing temperatures, right, we know evolution can adapt on the millions of years time span to carbon dioxide concentrations much higher than they are today, right? But can we adapt to changes in the decades or centuries time frame? And that's what worries people. So let me just go through, so I showed that CO2 is increasing, but there's also clear signs that CO2 is changing the absorption of IR in the atmosphere. So in this figure 4 here from Harry's in 2001, what they're showing is the change in outgoing solar radiation in the IR, and they're showing the change between 1970 and 1996. And what they're showing here is that there was a change in how much IR could leave around the 700 wave numbers, and that was due to CO2. And then you see these little small spikes because of CFCs, some ozone, and then you also see more spikes due to methane, right? And what this is saying is that it's the increases in CO2 and methane, and to a small amount, the changes in CFCs, and also the destruction of the ozone, which are changing the amount of solar radiation that can get out. And because of that, what we're finding is that this is the clear evidence, when you follow all this through, that it's human-induced emissions of CO2. The CO2 is changing outgoing solar radiation, and hence should be affecting the temperature. And I'll be getting to that in the next slide. But let me just show you kind of what I mean by the outgoing solar radiation. So in the graph on the right, what we have here is the red is the sunlight coming. This is in the UV visible, and partly going into the infrared. This is the energy from the sun, some of which gets scattered, right? And then in the blue we have the outgoing thermal radiation. And what you see here is that let's first look at water vapor. Water vapor actually will cause it to be nearly impossible for IR to leave at wavelengths greater than about 20 micrometers, right? That water is just absorbing all the IR that's trying to escape that has wavelengths less than 20 micrometers. Sorry, greater than 20 micrometers. We also see carbon dioxide. And you can see that the carbon dioxide is located in a point that's in the tail of the water vapor region. So one thing clearly to point out is that if you didn't have water vapor, the effect of CO2 would be very different than if you had a lot of water vapor in the atmosphere. If you have a lot of water vapor in the atmosphere, putting in more carbon dioxide doesn't make all that much big of a difference. But if you don't have any water vapor, that CO2 can have a much different, adding CO2 can have a much different effect. Especially because as you increase the CO2, what you're doing is you're increasing the width of that hump around, I think that's around 18 micrometers. If there was no water vapor, you'd be increasing. Well, you're going to increase the hump on both sides, but when there is water vapor, you're only effectively increasing it on the left side, because the right side is already saturated because you have all the water vapor. So what I want to point out here is that we should not expect all regions of the globe to increase at the same temperature, right? Global warming does not mean that the entire globe warms at the same rate, right? And it does not mean that it's going to warm at the same exact average rate over time, right? These are all very non-linear. There's lots of feedbacks, right? What I want to point out here is that because of the overlap with water vapor, the greenhouse gas effect of CO2 is most notable when there's little water vapor in the atmosphere. So what it means is that you should expect nights and winters to warm more than summer days. Right? So winter nights in Alaska, you should expect to warm a lot more than summer days in Florida, where it's really, really humid. Right? And that's what we're finding. We're finding that the Arctic is warming much, much faster than Florida on average. And so in this sense, our expectations and measured values are in agreement with each other. Right. Global warming, and so in this sense, there are some positive benefits to global warming in the sense that I think most of us would want our winter nights to be warmer, right? If it only had a slight effect on our summer days, right? But there's still the fact that no matter what, our summer days are still going to get warmer, right? And there are major issues if summer days continue to get warm, and which will cause droughts and other issues. Okay, so here's another graph just showing between 2003, 2012, and once again you can see major effects where there's CO2 and methane, showing that it's the increase of these gases in the atmosphere that are changing where IR radiation can get out of the atmosphere, at what frequency, and hence to compensate for that, the temperature has to increase in order to get the radiation out. In this slide, I want to point out that there are some predictions because in the theory of man-made global warming, because of human-induced CO2 emissions, we should actually expect that the warming should be taking place more at night than in the day. And the reason for this, as I talked about in a prior slide, there's overlap between the frequency at which CO2 absorbs and water vapor absorbs. And because of that, if there is already water vapor in the atmosphere, CO2 cannot have as big of an effect as if there weren't water vapor. So we should expect that when it's warm out and there's more water vapor in the atmosphere, then we should expect that CO2 should have less an effect, i.e. the places that should warm the most are the Arctic at night in the winter. Right? The effect of CO2 should be most pronounced at the poles in the winter at night. So here's what we're finding. Here's actual data between 1950 and about 2005. And what we see here is that the number of extreme cold nights decreased, and the number of extreme cold nights decreased more than the extreme cold days. And we found that warmer nights extreme warm nights increased more than extreme warm days. So in both cases, we see there wasn't as much effect on day temperature as there was on night. So here's a prediction from the theory, and that passes the prediction that nights should be warming more than days, and that's what we're finding here. What we saw was maybe a 1 degree change in temperatures globally, but in the Arctic, we've been seeing about a 3 degree change between 1880 and about 2010. Right? The temperatures are changing much more rapidly in the Arctic than they are across the globe. And of course, one reason to explain that, as I said before, is that when you don't have much water vapor to start, the effects of CO2 are that much more drastic. There are, of course, other issues such as the reflectivity of the ice changes as the temperature warms. You have these feedback effects. What used to be a mirror, if it's no longer a mirror, if you melt snow and you reveal the grass underneath, this is providing a feedback mechanism to increase temperatures even more than just by that CO2 effect. Okay, and then one thing I want to point out is this is very, very recent data. Late in 2013, some physicists actually went through, and they went. So the Met Office is the Royal Metro, like the UK Royal Meteorological Society, has been putting out data on global average temperatures. Of course, the Met Office hasn't been including areas like the Arctic. Right? So on this graph of the globe, you can see in white are those areas not covered by the Met Office. Well, if you don't include the Arctic, it kind of looks like there hasn't been much of a temperature change over the last 10 years. What these physicists were able to show was, well, if you actually include the Arctic and parts of Africa and other parts of the globe that weren't included in the Met Office, you actually find a sizable increase in temperature over the last 12 years, right? There has not been like a pause in global warming. It's continued. It's not nearly at the same rate as it was, let's say, between 1980 and 2000, but I wouldn't expect it to be the same rate, right? What matters for carbon dioxide concentrations, as we'll see, is the logarithm of the concentration, right? So let me go through this next slide. Predictions don't predict linear increases in temperature for a linear increase in the concentration of CO2 in the atmosphere. They expect a logarithmic increase. And that's just due to that absorption band grows logarithmically when you're already kind of at the point where the center is saturated. So we shouldn't expect linear increases, right? We should expect some kind of logarithmic increase. Of course, if we continue to put CO2 in the atmosphere, we're going to see some very high. We could potentially see some very high concentrations that would cause really high increases in the global average temperature. And so on this plot on the right, you could see as you increase the concentration, right, we're getting into temperatures that could be between 4 to 6 degrees higher on average. Of course, it means that the winter nights are going to be increasing slightly above average, and summer days will be slightly below average, but still, we're going to start having issues if our summer days get anywhere near to a 4-degree increase in temperature, in degrees Celsius. So ultimately, we're going to be needing to cap and start either decreasing or getting the CO2 concentrations back to kind of either where they are now. Perhaps we don't need to go back to how they were in 1880s, right? As I said before, there have been some benefits, such as the winter nights warming, but there are also plenty of problems. And of course, one of them, as I said before, was that sea level increase rise, right? As the Arctic melts, land-based ice and snow, when that melts, that gets into the oceans and increases the sea levels, right? And we're already starting to see places being affected by higher sea levels. Now, this is particularly the case in parts of Vietnam that are flooded, New Orleans, right? Places that are low level are highly susceptible to increased damage whenever there's hurricanes and tsunamis of the sort. So this is something that is affecting people right now, and of course you have to answer the question, is it fair for me to put carbon dioxide into the atmosphere, even if I myself perhaps wanted to live in a world that had warmer winter nights, right? Is it fair for me to put CO2 into the atmosphere if it's causing higher sea levels and causing places like Vietnam to flood, right? And ultimately, if you care not only about your own short-term economic growth, but you also care about the economic growth of all people, and let's say all life on Earth, you have to I think you come eventually to the conclusion that you need to put a cap on CO2 concentrations in the atmosphere. I don't know what that number is, but it's probably likely in some range between the 400 and 600 parts per million.
In this slide, I want to present some data that was in the 2007 IPCC, the Physical Science Basis chapter. And what I want to point out is that they did some post-dictions, that their models have come out, models that both include and don't include the additional CO2 from human beings, which labeled up on the top right as anthropogenic, plus natural forcings, and then you can see in the bottom left you have post-dictions of what the temperatures would have been if it had only been natural forcing, such as the sun, volcanoes erupting, natural kind of weather cycles. And then in both cases we see in black is the actual observations. And what you can see here is that that you can post-dic, or like i.e. the opposite of predict, right? You can go back, and if you include CO2 forcings, you can predict what the temperatures would have been in the past, and they match up fairly well compared to actual observations, except for around the 1940s. It's really unclear what was happening in the 1940s, but there was a decade-wide it's unexplained both by natural forcing and natural forcing plus anthropogenic CO2 emissions. But I do want to point out the temperatures, if there hadn't been the extra CO2 around, temperatures would have started dropping in the 1960s. And but observations don't show a decrease; they show an increase from 1960 to 2000. And this is where you need something that's actually increasing during that time period, and that's what the CO2 is providing. So this is once again a good confirmation that the theory that it's man-made emissions of CO2 that are causing increases in the temperature. This is once again a successful post-diction that this is another kind of check that this theory makes sense.
Okay. Now, as I said before, if you look at the net effect of global warming, the net effects are not significantly bad. So there's a Richard Toll actually went through and he looked at he did a meta-analysis, meaning he went through and looked at all the economic analyses that estimated how much the welfare impact, meaning the impact on global GDP of a rise in temperature due to global warming. He looked at all the studies back when he did this in 2009. What he found was for a 1 degree rise in temperature compared to the temperatures in 2009, there might actually be a net global warming increase in GDP due to global warming. And that's either due to reduced deaths in the winter, opening Northwest Passage, or crop fertilization. However, after you get to over a 2 degree rise in temperatures, right? And remember that 4 degree rises are not unanticipated, or definitely are possible. Right? But once you start getting over 2 degrees, you start significantly impacting the GDP. And then you still, of course, always have to, and that's because of increased sea levels, droughts, and ocean acidification. Now, you always have to answer the question is, even though there may be a net economic gain, is it fair for one person to gain and one person to lose, right? Right. As I said before, there are places like Vietnam that are affected by flooding due to higher sea levels, right? Is it fair for us to still emit CO2 in the atmosphere and cause somebody in Vietnam to be flooded, even though there may be some benefits such as reduced deaths in winter, opening of the Northwest Passage, and crop fertilization? These are really, really tough all I'm trying to point out is these are tough questions that we're trying to address individually. We're trying to address the society, like in societies, and we're trying to also address globally through our politicians. What Toll did calculate was that if you assumed a 3% discount rate, and later in this course I'll explain what a discount rate means, but essentially if you use a 3% interest rate, the net present damage of CO2 is about $20 per ton of CO2 in 2009 dollars. And that's actually not too far from from the price on that's expected on let's say from various cap and trade or CO2 taxes that are coming out across the globe right now. In the U.S., the government publishes what they call the social welfare impact of CO2, and these the impact depends greatly on what you use as your discount rate. And if you take this 3% one, the government is estimating that the cost of CO2, meaning how much you would have to tax it to effectively get rid of, or how much you'd have to tax it so that you could use to offset those people who are affected, say, by the flooding or by higher acid concentrations in the or by, say, just higher temperatures in the summer or by droughts, right? How much would you have to tax the emissions of CO2 so that you could pay for all those damages? What they've estimated are numbers in the 33 to 70. Of course, that number increases with time, and I think part of the reason that number increases with time, as I said before, initially you may have some gain from greenhouse gas warming, right? And this is that learning to see the difference between a short term and the long term. In the short term, you have stuff like crop fertilization, but that goes away after you hit a certain concentration of CO2. Yeah, it's nicer having winter, less deaths in the winter, but once the winter gets to a certain point, that goes away, and then you just have the issues of the summer being so hot that people are dying in drought because of droughts. So that's part of the reason why that number increases with time. Okay, so let me now talk about which countries are emitting carbon dioxide into the atmosphere. And historically, the U.S. was the largest emitter of CO2. But in 2008, the U.S. was surpassed by China as far as CO2 emissions. And of course, on a per capita, meaning per person, in 2008, when the China surpassed the U.S., its per capita emissions were actually 1/4 of the U.S. Right, so when you kind of look at the per person kind of effect, the U.S. is still one of the major emitters of CO2. In this slide, I want to go through some of the ways of tackling or capping and making sure that we don't go over a certain concentration of carbon dioxide in the atmosphere. So I'm going to talk about 3 different types of regulations, all of which have actually been tried at various points in time. And so these are kind of I want to talk about the 3 different kind of classes of regulations that we've seen so far. The first one is when you put a max limit on CO2 emissions per amount of electricity generated at a power plant. And this, as we speak, is what the EPA has proposed to do in the U.S. So let me talk to you a little bit about the history through this, and then we'll talk about where it potentially may be going in the future in the U.S. So this largely got started when in 2007 the U.S. Supreme Court decided in a 5-4 case that the EPA could regulate carbon dioxide and other greenhouse gases as pollutants under the Clean Air Act. The Clean Air Act was used to control mercury, has been used to control mercury, NOx, SOx, and particulate emissions, as well as a number of other
noxious chemicals, all of which provide either local or regional impact and direct health effects. So of course, the reason why it was a very close decision was that CO2 is not a local pollutant. It's of course, a global problem, which means that it has to be solved globally. You can't just clean it up from one factory and solve the problem in the region around the factory, right? This is a global problem. Carbon dioxide emitted in China has just as much effect on flooding in New Orleans as a power plant in New Orleans, right? So that's I think why it was so closely why there's such a controversy over this. It is a very different type of pollutant, but we can argue that it still has health effects, because if people are flooding because of higher sea levels, which came from the Arctic melting, then people are being damaged. It just it's obviously not a direct causation of any one power plant to any one impact. So, okay. So, but in 2012, the ruling was backed again by the U.S. Court of Appeals. And at no point in time did Congress pass, Congress and House, and then so no legislation was actually approved through the House and the Senate and approved by both of those legislative bodies. So only action so far has been taking place in the judicial side in the U.S. So because of this ruling, the EPA put out a proposal, and they put it out twice. Put it out once again in January of 2014, and here they proposed a limit of 1.1 pounds of CO2 per kilowatt hour for coal power plants, and 1.0 pounds of CO2 per kilowatt hour for natural gas power plants. It is currently, as we speak, it's January 2014 right now, it is in the point in time in which the EPA is receiving feedback from people living in the U.S., and they are then going to decide, perhaps by June of 2014, whether or not to actually implement this law. So that's where it stands right in the U.S. We're on the cusp of potentially actually having federal regulation of CO2 from power plants. And I do want to point out this only applies to new power plants. It doesn't apply to cars. It doesn't apply to chemical factories. Chemical plants doesn't apply to CO2 that's emitted from concrete or methane from cows or anything like that. It's only new large power plants. Okay, now the second type of regulation I want to talk about is when you fix the amount of emissions and allow the cost to vary. So this would be as if you fixed that there were a certain amount of permits, and each permit allowed you to emit a certain amount of CO2. And that's what's happening right now in the European Union emissions trading scheme. And the actual cost of these permits varies anywhere from $4 to it's been up to $20. It's in the range between $4 and let's say $20 per ton of CO2 over the last couple of years, and that will depend greatly on how many permits they issue in the next year. That will affect the price. So you can see in this one, you're capping how much can be emitted, and you allow companies essentially to bid on what the price is going to be to purchase those permits. Now, another option would be to just impose some kind of tax, where you put a fixed amount of dollar on the tax. What that means is that the amount that gets emitted is not fixed, right? That amount is just dependent on the companies. They can emit as much as they want as long as they pay the tax. So in 2012, Australia implemented such a greenhouse gas emissions tax, and they put $24 per ton of CO2 on the price. But this tax did not last very long and was dropped shortly thereafter. So these are the three main type of regulations we've seen so far. Okay, so now what I want to do is switch gears a little bit and talk about the fuels that we will and we won't, the fuels we will be talking about and the fuels we won't be talking about in this class. So first I want to point out the fuels we will not be talking about, and those are the renewable energy sources. And this is partly because this is talked about in a different course I teach called Energy Systems Modeling. And in that course we cover a lot of time is spent on solar thermal because it does share a lot of the power plant design features as in some of the plants that we'll cover in this course, right? There's going to be heat exchangers, steam turbines, condensers, water pumps, and not much time is focused in that other course on wind or photovoltaics because there isn't that much of a similarity to the power plants in this class. I do want to point all these have their pros and cons. Not going to focus on too much because we're going to be focusing in this class on at fossil fuel power plants that meet those EPA regulations of about a pound per CO2, pound of CO2 per kilowatt hour. Here's just a little bit of information on renewables. Their amount has definitely been increasing with time. And that's pretty much all I want to say on this for right now. You can look up more information on this by going to the EIA, that's the U.S. Department of Energy's Energy Information Administration. Okay. One fuel that we will be talking about in this class because of its similarity to coal is municipal solid waste. Not that they're similar, but in necessary composition, but a lot of the plants that are designed to take coal can also be designed to handle municipal solid waste. So I'm going to talk to you a little bit about what municipal solid waste is and how much of it is generated. So in 2010 in the U.S., 250 million tons of MSW were generated, which corresponds about 2 kilograms per person per day. Right, that's a lot. 2 pounds per person per day. Of that municipal solid waste, about a third is recycled, a little bit over half is landfilled, and then about 12% is combusted in waste-to-energy power plants. The energy density of the paper part is about 16 megajoules per kilogram, and the plastics part is about 32 megajoules per kilogram. If we go over to the graph on the right, you can see the municipal solid waste is made of a mix of paper. Of course, we've got glass, metals, which would need to be taken out and recycled. We have plastics that can be sent to waste energy, just like the paper can be sent. Rubbers, textiles, wood, yards, trimming, and food scraps. All of this can be then sent to either waste combustor or waste gasifier. If it's combusted, if you took all of the combustible parts of the municipal solid waste, you could hypothetically generate about, and taking the efficiency of a Rankine cycle, be generating about 10 gigawatts of electricity. Now, for comparison, I want to point out that U.S. coal power plants were generating about 250 gigawatts of electricity on average. So there's not enough, I do want to point here, there's not enough municipal solid waste to completely get rid of all coal power plants in the U.S., right? It's there's at least an order of magnitude difference here. But what I want to point out is if you're in a region, you can get paid to take municipal solid waste, and this can definitely affect and help the economics of a combustion, like a Rankine cycle power plant, if you could design it to handle some amounts of municipal solid waste. I'm not going to be spending much time in this course on oil, but I just want to point out a few things which I think are important. And And the one thing is I want to just make sure that everyone in this class is aware that most of the oil that we consume in the U.S. was either produced in the U.S., right, 60%, and this is statistics from April 2013, 60% of the oil consumed in the U.S. was produced in the U.S., and a total of 75% was produced in either the U.S., Canada, or Mexico, so basically our neighbors, right, or ourselves. 75%. 5% comes from Saudi Arabia, about 4% from Venezuela, 2% from Russia, and 14% from others. And that others is mostly OPEC. But we can see here is OPEC countries are on the order of 20% of the total oil being consumed in the U.S. Right? We're not talking about huge fractions here, right? Most of the oil that we consume is actually produced in North America. But I'm bringing this up just as this is one of those things that people often think that there's a lot more oil coming from the Middle East than there really is coming into the U.S. So the other thing I do want to point out here is that we will likely still be using oil long after we've stopped emitting CO2 in the atmosphere, and this is because we're still going to be needing oil for making plastics and other synthetic chemicals. And so I just want to point out that crude oil and drilling for crude oil will be around for a long time. It's a great building block for a lot of chemicals, and it is, in the words of Ken DeFays, a geologist from Princeton University, our grandkids are probably going to be thinking, why the heck did we ever put this in our car when it is so useful for making synthetic chemicals, right? And that's my guess of what our grandkids are going to be thinking, where they're going to be thinking, why the heck would we have ever put this in our cars when we could have run our cars on like hydrogen or electricity and save the carbon compounds for stuff that we want to actually use for building chemicals. Okay, one fuel that we will be talking a lot in this class is natural gas, and that is because right now natural gas prices in the U.S. are so low that it doesn't make sense to build any other type of power plant than a natural gas unless there's some type of subsidy involved. And it's just because the price of natural gas is so low, and the price of and the cost to build a natural gas power plant is so cheap that you can effectively pay off the loan in a couple of years, and you can also buy natural gas futures a couple of years out, which means that it's almost a no-brainer right now to be building these. What makes it even more of a no-brainer is that the EPA regulations have been designed so that natural gas combined cycle power plants can be built and still fall under the emissions emissions regulations. So it is likely that as long as the price of natural gas stays low, that this will be the chosen type of power plant. And because of that, we're going to spend a lot of time in this class on how do we design a natural gas combined cycle power plant, how do we estimate the cost, and so that we can eventually estimate the rate of return on investment. So let's talk a little bit about natural gas itself. Right, it's a fairly low carbon to hydrogen ratio fuel. Right, it's a 4-to-1 ratio of hydrogen to carbon, as opposed to coal, which is there's actually more carbon than there is hydrogen in coal. And so what has been occurring over the last couple of decades has been that the techniques for horizontal drilling and fracturing have greatly improved. Part of this is due to a company called Mitchell Energy, which was working out in Texas, out in the Barnett Shale, and they were perfecting a technique out there. Eventually spread. Other companies started getting involved. And you also have some input from government agencies who have been looking at this more from a mapping out as far as a lot of government agencies, either the DOE or the USGS or the EIA, have kind of gone through and done estimates of total reserves, economic reserves, engineering reserves, just to figure out how much of this is under the ground. But it was largely companies like Mitchell Energy that were perfecting this. And what happened was, as they were perfecting it in the 90s and then in the 2000s, reserves of natural gas actually started increasing more than natural gas consumption started increasing. So what happened was, between 1980 and about 1995, reserves in the U.S. were actually dropping, as when you take the ratio of reserves to consumption. That ratio was dropping from about 12%, from 12 years down to about 8 years. But starting around 2000, that ratio started increasing, and now is sitting up near the 12 years. We're still not talking about a large number here, meaning we only have 12 years approved reserves compared to our consumption. But it doesn't mean we only have 12 years of fuel, because obviously back in 1990, when there were about 10 years, right, it should have run out in 2000 if that equation, but we didn't see the fuel, natural gas, it was just disappearing by 2000, of course, because by 2010 that ratio went back up to 12. So it's more important to point out that these numbers are small enough that it can lead to price volatility, right? When you're not sure that you have 100 years of reserves, that definitely can lead to a lot of price volatility, and that's what you see if you actually look at historical prices for natural gas. It's very, very, very volatile compared to coal. Okay. I do want to point, because we're here in Pittsburgh, Marcellus shale drilling began around 2005 and really started picking up around the 2009. And we're going to talk a little bit about the economics of drilling in the Marcellus shale, because we're here in the Pittsburgh region. And one thing I want to point out is the profitability of wells greatly depends on where you drill. There appears to be a kind of this dividing line between what's called the wet gas and the dry gas regions, and with the wet gas being kind of on the northwest, dry gas in the southeast. And let me start off with I'm going to start with the bottom bullet and talking about what I mean by wet gas. Wet gas doesn't mean that there's water. What we mean by wet is that there are higher hydrocarbons in the natural gas. So in the wet gas region, you can sometimes drill and get a gas composition that's 75% methane, 15% ethane, 5% propane, and 2% butane, and even some amounts of higher, going all the way up to octane, like in the 0.1% kind of region. Those higher hydrocarbons, as soon as you start chilling the gas to room temperature and to slightly below room temperature, they will condense out, and that's what they mean by wet gas. Is that there's a lot of gases condensing at temperatures not too far below room temperature. And of course, there is one problem with this wet gas, is that there's a lot of ethane, and it is very, very difficult to separate ethane from methane. And for this reason, companies have proposed building in this region, wet gas region, what are called ethane crackers, or ways of trying to get rid of the ethane and turn it into ethylene, which can then be turned into like polyethylenes or the polypropylenes, eventually converted into. But these are the building blocks for polymer chemistries. So I just want to point out that this wet gas has a lot of hydrocarbons, and actually when you, a lot of your main revenue is actually the higher hydrocarbons. So when you drill a well in the wet gas region, most of the money is coming from these higher hydrocarbons that you just condense out. and then the methane and ethane are kind of this waste product that you just kind of sell onto market. And because of that, the price of natural gas in the Pennsylvania region is actually well below the Henry Hub average. And prices of natural gas in Pennsylvania are really, really low compared to global averages. The Henry Hub down in Louisiana is low compared to global averages, but in Pennsylvania it's even lower. And the reason is that there's this wet gas region where people are just trying to get rid of the methane, and they'll accept almost any price for it. And because of that, because effectively the supply is so high, it keeps the price down. But because that price is so high, if you are in a dry gas region where most of the natural gas is actually methane, what you can actually get is that it can, with the natural gas prices near $3 per gigajoule, it effectively kills your return on investment in the dry gas region. So it's one important thing is if you go into this field is that the geology is so important in this region, because you can be you can be in the same Marcellus shale but get completely different type of gas coming out, and that gas will greatly affect your profitability. Okay, so next we're going to switch to the other main fuel source that we'll be talking about in this course, and that's coal. And the reason we're talking about coal is it has a stable and a very, very large supply. So let's talk first about the consumption of coal. This graph here shows you consumption over the last decade has been rather stable and flat, and it's the number is about 550 millions of ton oil equivalent per year is how much coal is consumed. We're talking millions, hundreds of millions of tons of oil equivalent of coal. And when you look at the reserves and then divide that by the production, what you find in 2011 was that the reserves to production ratio was 239 years. This number is so large that it's effectively not going to change drastically in any 1 year unless we were to redo our reserves ratio. But when that number is so high, there's almost no need to even go through another a change. Like when the reserves are 240 years, it's telling you that we have a large supply, much larger supply than we're going to ever be consuming in any even 1 decade. And I want to show in the top right the picture. This is a surface coal mine in the Powder River Basin in Wyoming. This Powder River Basin area is now the largest supply of coal in the U.S. And the reason is that it supplies a very low sulfur coal, and it can be fairly easily accessed. If you see here, you don't have to remove that many feet of dirt to get to a seam. And once you get to the seam, it's a fairly thick seam of coal that you can then dig out. And as opposed to in subsurface mining, you can get all the coal out. You don't have to leave columns behind. Right? And then after you finish, you just pour the dirt back into the hole, and then kind of replant the surface, and you can get this back looking almost like it was beforehand. Okay. Now, just as a reminder, in the U.S., we were consuming about 550 millions of tons of oil equivalent. In China, in 2011, they were consuming about 2,000, so almost 4 times as much coal as the U.S. And their consumption of coal doubled between 2003 and 2011, right? A doubling, which is in effect in 8 years, which is absolutely huge. So China consumes a lot of coal, and because of that, and because they don't have as much reserves as the U.S., their reserves to production ratio is only 31 years. Now, I do want to point out that the number that goes into the reserve part of that is highly uncertain. That data is held by the Chinese government, and it's not exactly clear how that number was arrived at, or even it doesn't get updated each year. So I do want to point out that 31 years is not some kind of fixed set in stone number. It's really unclear how much coal China has, but the 31 is kind of an estimate that the Chinese government is giving to agencies such as the BP, Statistical Review of World Energy. Okay, so now let's talk a little about what coal is. As we saw, natural gas can mean a lot of things depending on the amount of higher hydrocarbons. You can imagine it gets even more complicated with coal because there are a lot of different species in coal. So let's go through what coal is, right? Coal is biomass that has been cooked. And by cooked, what I mean is that it got buried a long time ago when it was biomass and likely sunk to the bottom of a lake. And if it sunk to a place in the lake low enough that there was no oxygen, so that there were no bacteria that could use that oxygen. I mean, if there was no oxygen, then bacteria can't consume the biomass, oxidatively consume it. Then what you would find is that the biomass would just start, eventually sediment from the top of the lake would bury the biomass, and the biomass would become part of the plate tectonics, and as the plate maybe went underneath the ground, the temperature and pressure would start increasing, and at some point in time the plate would come back up again, and the coal, kind of like going into an oven and coming back out again, would become cooked. So when the biomass doesn't spend much time underground, that's called peat, and peat is pretty much biomass. Looks almost exactly like, has the same chemical composition as biomass. If you put enough pressure, time, and heat, biomass will turn into what's called lignite. And here you start losing some of the hydrogen and oxygen that was in biomass. If you cook it longer, you get something called subbituminous. Cook it longer, you get bituminous. And if you cook it for an extremely long time, you get something called anthracite. And what's happening here is that the amount of oxygen and hydrogen are decreasing as you go from lignite to subbituminous and bituminous to anthracite. So by the time you get to anthracite, you are between like 80 and 97% on a mole basis carbon. And this, if you're at 100% carbon, you're at either graphite or diamond, right? And so anthracite looks very much like graphite. A lot of carbon ring structures. And so on this bottom right is a picture of the anthracite, and you can see it looks very much like graphite. Whereas this higher stuff looks more like cooked biomass, and looks more and more like mineral the longer you cook it. Kind of the same way that you'd be getting carbon black if you left something in a toaster oven. So that's the progression, and there are no real hard and fast rules between these, but there are some general guidelines for estimating based off of the carbon or oxygen content. Okay, next thing I want to talk about is the coal locations, and what I want to point out here is that different regions are producing different types of coal. In Appalachia, which is largely western PA, eastern Ohio, and West Virginia and parts of Kentucky, it's largely a bituminous coal. Typically there's some sulfur in the coal, and but it was cooked for fairly long. It was a bituminous coal. And in certain regions, you actually get anthracite coals. And if you notice on this graph, there's only about 3 major locations of anthracite, 2 of which are in Appalachia. And this is one of the reasons why building steel mills was occurring largely in places like Pittsburgh, was that there was a local supply of anthracite. But once again, part of the reason the steel mills were being built in Pittsburgh was because of the rivers. The iron ore was not
coming from the Pittsburgh region. The iron ore was actually coming really far away, typically coming from Minnesota. But the anthracite was local. And so that's the Appalachia region. There's still a fair amount of coal being mined in this region. The next one I want to talk about, it's a bituminous coal, but there's an Illinois region. Here what I want to point out is the Illinois region, coal mines got shut down when the Clean Air Act was passed because the Illinois coal typically has a lot of sulfur, and they found it was cheaper to mine coal elsewhere that had low sulfur than to try to build sulfur capture equipment to be able to handle the Illinois coal. So coal mining in Illinois is essentially stopped. It could potentially pick up again in the future with technologies such as coal gasification, in which sulfur capture can be done very, very, very cheaply. And in which case, it is one of the reasons why coal gasification plants are being proposed. They haven't been built yet, but are being proposed in the Illinois region, and that's to take advantage of rebuild the coal industry in Illinois by using a technology that can handle high sulfur coals. Okay. The next thing I want to talk about is this dark green that appears in the Wyoming region, and it's this shape, up kind of taller than it is wide, and that is the Powder River Basin, and that is where the majority of coal in the U.S. is being mined right now through surface mines. It is a subbituminous, so it's a younger coal than what's being mined in Appalachia. It's also a very, very low sulfur coal. And there's also some lignite that's being used, that's being mined either in North Dakota or in the Gulf Coast region. So that lignite's a younger coal even than the subbituminous. So here's a breakdown. So anyone who's interested in knowing the actual composition, I've taken shown the composition both on a weight and on a mole basis of two types of coal. The first is a Pittsburgh number 8. So that is a bituminous coal from the Pittsburgh region. The second one is the Wyodak-Anderson, which is from the Powder River Basin, and that is a subbituminous coal. So I want to point out the differences here between the Appalachia bituminous and the Wyoming subbituminous. You can see the carbon content is higher in the Pittsburgh coal, and the oxygen is lower. So what we have here is that it's an older coal, more oxygen has been removed, leaving carbon. And both have nearly the same amount of nitrogen. It's about a 1% on a weight basis. There's a very big difference in the sulfur content. 2% by weight for Pittsburgh and a 0.6% weight for the Wyoming one. And that is the low amount of sulfur in that Wyoming coal is one of the reasons that you could actually put it into a power plant and meet EPA guidelines on regulations on SOx emissions without needing sulfur capture equipment, because that number is so low. The Pittsburgh one is high enough that you actually do need some kind of regulation. You actually need some equipment to capture sulfur dioxide species in order to meet EPA regulations. The other thing I want to point out is it's also that Wyodak-Anderson can also be a fairly low ash content, around like a 4% or so weight ash. And by ash, what I mean is all the inorganic species, and that's mostly silicon dioxide, aluminum oxide, and then some calcium, iron, and other smaller amounts of other species. Here's just a schematic of the different types of mining. As I said, the surface mining is what's happening in the Powder River Basin in Wyoming. Subsurface is largely going on in Appalachia, like West Virginia. In that subsurface mine, you actually have to leave some kind of support, either the coal itself or some other support, to hold up the weight of the mountain above it. Whereas in surface mining, it's inherently less
dangerous. Just inherently less dangerous because it's out in the wide opening. Now, with that having been said, because subsurface mining is confined, it means that you can capture all the methane that comes off of coal and actually either combust it so you don't have methane emissions. Whereas with surface mining, unless you somehow remove the methane beforehand through some kind of drilling technique, like a coal bed methane technique, you have the potential of having methane emissions as you start drilling, as you start mining in let's say, the Powder River Basin. Okay, and so since this is the course motivation slides, I want to talk to you a little about one of the main focuses of this course, which is how do you capture CO2 and what do you do with it after you've captured it. So what I want to point out here in this overview slide is just to get us talking a little about what are some of the options. And so depending on what you do with the CO2 can greatly affect the profitability of the power plant. The cost to inject CO2 underground, if you were to have to drill the well, would be between about $1 and $8 per ton of CO2 that you'd have to pay to sequester underground. But you could potentially pay somebody, and well, somebody could potentially pay you, and that number is typically between about $10 to $20 per ton of CO2. If you are in a region like Texas or North Dakota, where there are CO2 pipelines, you can actually get paid, and a oil company will take your CO2 from your hands and use it in enhanced oil or enhanced natural gas recovery. Mostly this is an enhanced oil recovery because the CO2 can basically be used as a foam, because the CO2 basically can be turned into foam at high pressures underneath the ground, and that foam will push out oil from the pores in which it's residing. So those are some of the costs. I do want to point out people have talked about mineralization, and those where you take kind of alkali earth silicates and turn it into alkali earth carbonates, but so far nobody has shown this to be even remotely cost effective. Turns into roughly kind of prices on the hundreds of dollars per ton of CO2, which is, we'll find this number is absolutely an order of magnitude too large. So in this course, this is a lot of information on the slide. I just want to put this up here. This is a slide from the National Energy Technology Laboratory where I work, showing the different technologies that we're working on. There's a number of different solvents, sorbents, and membranes that are being looked at, all in different kind of times of commercials, times before they could become commercial. And so these are some of the ones we'll be talking about in this course. Here's a working example of an amine solvent capture process at a coal power plant on the left, and then from a natural gas power plant on the right. These, when you see these are amine towers, and amine solvents, or by amine I mean basic solvents that have amine structures in them, like NH2 bonded to something. That basic structure can capture acid gases like CO2, H2S, or NOx and SOx. So it's been already being used in both the coal industry and the natural gas industry. So if you'd like some more information, here are some websites. As I've said before, I used a lot of the data in calculating the figures is coming from the BP Statistical Review of World Energy, and I highly suggest you take a look at that. They put one out every single year. Of course, there's a lot of information from government agencies such as the EIA or the IEA. And definitely take a look at the IPCC's reports that come out roughly about every 4 to 5 years.